graph clustering. So, so last week we talked about modularity, and how this is a useful notion to define clusters in a graph. Does anyone like to venture a reminder to me as to what modularity was? If I have to walk all the way there to look. Anyone? How did we? What was the idea by which we wished to define modularity? How did we think about this issue? Right? We were trying to do. The idea was to come up with some notion of a cluster in a graph, and so modularity was the way we wanted to capture this notion of a cluster. So how do we do it?
And maximize basically the weight, or what was that? Number of connections inside the cluster.
Well, let's make it simpler. Let's say I have a graph and I have some subset, and I can ask what the modularity of the subset is. Anyone remember?
Average weight. What was that? Average weight.
We needed something first before we could even do this. So there was a concept, right? The concept became a formula, but there was a concept. What was the concept?
That's what I'm trying to remember from last week.
Reduce the.
That's what I'm trying to remember from last week.
It was good to remember.
So I wasn't here most of the time, but wasn't the idea that if you look at the edges, you should have much more edges within the group than out of the group?
Was that what it was? It wasn't quite that, was it? It was almost that.
Minimize the number of connections which are going outside. We are giving zero weight to those.
No, that wasn't it either.
You should have
In fact, we will be talking about that today, but that's
more
not what we're talking
connections
about.
inside than outside as compared to random.
Ah, okay. So something about random. There was some notion of random, and this was being measured relative to random. What is random?
It was the Erdős model, right?
Was it?
Was it?
Was it? Was it?
I don't-
Was it? Was
It
it?
was, yeah.
I don't know. What is it? What is the model that we are thinking of in terms of random? We had some notion of what it means to be random. We talked about the Erdős model, and we decided that we didn't like it very much for various reasons. So we moved to something else. So first of all, why didn't we like the Erdős model that much? Yes? Your question?
No?
So what did we like about the Erdős model? What was the Erdős model that we didn't like? Before you hate it, you must know what it is.
Had a skinny tail.
So does a rat. But what is the Erdős model?
But you make an edge proportional to the degree of the knot.
No. That in fact is the not Erdős model.
Which model?
Sorry?
Not.
That is the not Erdős model.
Just P.
Pick up P equal probability.
So there's some fixed parameter P, and you pick an edge with probability P, independently for all edges. And as John said, the problem with this model is that it has a skinny tail. In other words, if you look at the degree of a vertex, you can say its average degree is going to be P times n minus 1, an expectation. And this is a sharply concentrated Bernoulli sum. So it's going to be very, very sharply concentrated around that value, which means the likelihood of it being anything more than that or less than that is going to drop off like crazy, exponentially in particular. In other words, skinny tails. Right? So this is the degree distribution. And so we didn't like that. Why? Why didn't we? What's wrong with skinny tails? Yeah. Unless you don't like rats, but you know, what's wrong with squeak tails? Why is it a bad thing? Yes? Why would it be bad to use this actually the Erdos-Reddy model of randomness to capture the notion of random in a graph? Why would a squeak tail be a bad thing? There's no mathematical reason per se, but there is another reason.
I know to social networks why this is a bad model.
Why is it a bad model?
Because it doesn't mimic really the real world data.
It doesn't mimic real world. What?
In terms of what happens in most of these networks, you have power law or some kind of power law
Right.
distribution over degrees in the nodes.
So the point is that
size of communities, whatever it is.
so the model that we described as being random is not random because it doesn't capture what we tend to see in the graphs we actually encounter. So most graphs that we actually encounter have a degree distribution. So this is the frequency and this is the degree. That's not like this, it's more like this. It's fat-tailed. The degrees decay off, but don't decay off anywhere as quickly as what this model will predict. So if you're saying the Erdos-Reddy is your model of randomness, then you're going to get very distracted. Every graph is going to look supremely interesting because it looks so different from this model. Whereas what you should be saying, no, this model is not the right model. Right? So this is the problem with choosing a model, right? You need to choose a model that does capture the baseline of what you expect from your data or what you think you're expecting from your data. If you choose any arbitrary model, that's not going to work very well. Okay? So then we came up with a different notion of random. And this seemed to relate more to degrees. So what was that? What was the idea for this other random model of a graph that we're going to use to define modularity? Any thoughts?
I mean, at a high level, it had to do with looking at the probability based on the number of, based on the degree of this node, the degree of this node.
So let's be
that they
concrete.
match.
So we have a U and we have a V, right? And this is node degree U and this is node degree V. What was the idea we were playing with here? That when do we put an edge between them? When do we connect this edge?
When basically you've been able to choose that there should be an edge between U and V coming from V, and similarly from U.
Right, so something roughly like the probability of this edge is something like du times dv over 4m squared.
Yeah.
2m times 2, right? And the idea was that, okay, we're not going to try to just build a model from scratch with one parameter. We're going to give you actually a lot of parameters, the degrees you expect to see on every vertex. And then based on that, you're going to construct a graph. So this is called the configuration model, and this was a model that we thought was better at capturing how real graphs look. You can actually get better degree, you can choose any degree distribution you want, right? You can say, I want a power law degree distribution. You put that down, and then generate a graph based on that. Okay? All right, good. So now that I have a notion of random, again, we're just recapping. How did we define modularity? Again, even intuitively, right? So what was the, so you mentioned already that you want to somehow compare this to random. We now have a notion of random. So what do we want to do? So in particular, let's say I have a graph and I cluster it into groups. Right? That's important. You're going to cluster things into groups. And now you're going to say, okay, this clustering has a certain quality, which you're going to call this modularity. What do we want to say? So the first thing I'll point out that we actually do not consider edges between groups. We're only considering edges inside a group. So in particular, let's look at any one group. What do we want to say here? That this is an interesting cluster if it's dense, right? But what does dense mean? Dense is relative to what you'd expect to see, right? It is denser than usual. That's what we're really saying. We're not saying it's dense. We're saying it's denser than usual. Well, we know what usual is, or we've decided what usual is. And so denser than usual should be more than this, right? And so the notion of modularity for a single cluster was something like over all pairs of vertices, you do something like you take that, whether there's an edge or not, minus the degree of I, degree of j, divided by 2m, and you put a 1 over 2m around this. Okay? And you put a delta function here, for xi, xj, which said, okay, are they the same cluster or not? So effectively, you're just summing this up inside each cluster. And if this number is big, then that means that you have a lot more edges than expected, so you're happy. If this number is small, so this becomes negative, then you have a lot fewer edges than expected. So in general, this number will range between -1 and 1, when this is, you know, very well clustered. This is noise, and this is badly clustered. Right? That was the basic idea. Yes? This is what we saw last time from modularity. Okay, good. Sorry?
Can you estimate those parameters, configuration parameters?
Those are given.
Huh?
Those are given.
No,
I mean, the model is defined by the parameters.
Yeah, but yeah, of course, but you need to define the parameters. So can you estimate those parameters just by looking at the raw statistics of the network?
Well, that's the thing, right? People have proposed various plausible degree distributions for actual graphs, and you know, you build your favorite power law Zipfian type distribution. You can imagine sampling this from that.
Yeah,
Right? That's-
but you need to create multiple of such sample networks, right? Random networks to
Sure.
get an average random.
Sure, yeah, but once you have a degree distribution, you can just sample them. Yeah. There are also more explicit generative models, these so-called stochastic Kronecker models, stochastic block models in general, that give you more explicit processes for, instead of this independence assumption, they're more correlated. You build blocks, you build these blocks, and so there are other ways you can generate models. So there are different models you can work with. Okay. So what I want to talk about today, so we talked about modularity, we defined this notion, and we talked about various algorithms. We described that you could have this greedy strategy where you find one cluster that's good, right, and then you split it up and repeat. And then I pointed out to you that there's a whole spectral analogy to this, that essentially you can look at the modularity as computing an eigenstructure and computing the top, you know, as usual, the top eigenvalue, or the smallest eigenvalue in a particular graph, right? So you essentially look at this graph, and then you look at the Laplacian structure of this graph, and this graph, the matrix you get from this is not semi-definite. So you have positive eigenvalues and negative eigenvalues. If you have positive eigenvalues, take the best one you have, and that gives you a split. If they're all 0 or negative, then basically you're saying this graph can't be clustered because it's looking very bad, which is actually nice because it gives you a natural way to stop clustering anything. And we discussed various ways you could go about it. That you take the top one and recurs, or you take a whole bunch of them and then you just split them up and so on. Okay. That's not, so I just wanted to review that because what I want to talk about today is a different way of thinking about the graph clustering problem. And again, as always with a lot of work in clustering, there's kind of the stuff that people do on the more applied side. I wouldn't call this very applied necessarily, but in the sort of non-sort of CS side, this came from physics after all. And then there's the stuff that's, so the theoreticians have looked at as another way of doing graph clustering. So I want to talk about that. And to do that, we'll be talking about notions called conductance and its relative expansion. Okay. Before I go on though, any questions about our brief review of modularity? Very brief review of modularity.
So and people that use this comparison of a random
Yeah.
graph to find interesting things, not
Yeah.
just for clusters, but for something that we call tips.
Sure.
So like around, I don't know, 4 or 5 years ago, I was working on figuring out whether the interesting tips if you use random structure.
Yeah.
And they use this in biological method to figure out whether interesting
Yep.
interactions.
They do all. Yeah. This is a. I mean, this idea of comparing to a random baseline is the basic notion of statistics. Right? You
Yeah.
have some baseline, you find with respect to that. So these are things that people look at.
It's really cool.
Okay. So, like I said, the notion of modularity is closely tied to this idea of a baseline. And that's very important. Because without a baseline, you can't define modularity. But suppose I insist that I still really do want to define some notion of clusterability or quality of a clustering of a graph without a baseline, or with a baseline that's more implicit in some sense. It turns out you can do such a thing. And so let's take for now, we have some graph. And we have weights on the edges. So there's some weight function on the edges. Okay, let's assume it's positive. So let me define some notions. So first of all, let me define the weight. So the weights are defined in edges. So let's define the weight of a vertex as the usual. So it's a summation of all, v comma u belonging to E, weight v. So this is undirected, so the ordering doesn't matter. So that gives you a weight of a vertex. And then what I'll do is, I will say the volume of a set is equal to the sum of all the weights of the vertices in that set. So think of the total volume as total, pipe capacity of a set. If you want to think of it that way. All the pipes going around edges, their pipes are the weights, and you sort of add them all up. Okay. Notice that if the weights are all 1, then this is just the degree of a vertex. And this becomes twice the number of edges in the set. Right? So total is 1. That's not entirely true. Edges in the set plus the boundary. Plus 1 times the boundary edges, because you add them all. So the volume is basically all of this plus this. Okay. So now what we're going to say is, we'll define the conductance of a set, any set, okay, as the following ratio. Think of it as the amount of flow going out, or the amount of mass that's going out, versus what's already there. So this is going to be the weight of S to V minus S divided by the volume of S. And with this quantity is the obvious thing. It's equal to the sum of all edges where U belongs to S and V belongs to V minus S. Okay. So this is called the conductance of a set. Well, it's called okay. So let's try to get some intuition about what this quantity actually is capturing.
It's the ratio of how much outside connections are compared to the outside and inside connections.
Right. So what would it mean if this number was small? For example, or in particular, what would it mean if this number is 0?
No connection.
There's no edges.
If this number is 0, then what does this structure look like?
Separate.
It's completely separate, right? It has whatever number of edges going inside, but it has nothing going out. That's a pretty good definition of a cluster. Okay. What happens if this number is very, very big? Let's say this number is 1. If this number is 1, what is going to happen here?
Everything comes in.
That means the volume consists completely of all the edges going out. So what does it look like? So this is what it looks like, right? This is not what you'd consider a good cluster, right? So in other words, the smaller the value of this conductance, the more of a cluster this begins to look like. And notice the difference here with respect to modularity. The modularity of a cluster depended solely on what was happening inside it. Because we said, well, based on random, we expect it to look a certain way on the inside, and it looks very different from that. Whereas here, what matters is not so much what's on the inside. I don't know how many edges there are on the inside. What matters is how these edges connect to what's on the outside. Right? Because I'm looking at this quantity here. So fundamentally, there is a difference in how we think about clusters when we use modularity versus when we use conductance. Conductance is an inside-outside notion. how different am I from everything else? Whereas modularity is how different am I from a random baseline. You see the difference here? Again, like with all clustering problems, right? The measure captures your intuition about what's going on. And here again, the measure is capturing a certain kind of sense of what it means to be a cluster.
But you are comparing to the volume, not the weight to edge, number 8.
The volume is the weight of the edges. Because the volume is the sum of the weights of the vertices. The weight of a vertex is the sum of all the edges going out from it. So you're actually adding up a whole bunch of edge weights here,
So edge inside that group is.
plus the edges going out. Yeah, so that's right. You can define, of course, a different notion called expansion, right, which we've seen, many of you may have seen before. So it's a very related notion. So the expansion of a set. So you take a set of vertices S and look at its neighborhood. So the neighborhood is all the vertices it connects to. So the expansion is equal to the size of the neighborhood, which just includes the set itself, just to be technical, divided by the size of the set. So this is a more vertex notion of expansion, right? This is an edge notion of expansion. This is a vertex notion of expansion. And these are related. I mean, well, they're related for interesting graphs, things like constant degree graphs, obviously. For arbitrary degree graphs, so these are not as related as nice. So we have seen this notion before, and this can sometimes get used well, but we're talking about this right now. So again, conductance is a way to measure the quality of a cluster by looking at what it looks like with respect to the outside. If it's very cohesive on the inside compared to the outside, its conductance will be small, and that'll make it more cluster-like. If it's very diffuse and everything just goes out, it has high conductance because everything just diffuses out, and therefore it will not be cluster-like. The word conductance, really, you can think of it as coming from a sort of a heat flow or electrical flow analogy, right? The more connections it has to the outside, the more heat will conduct essentially away from the set and diffuse it out. The less connections it has, the less conductance it will have. And that's where the word comes from. Okay? All right. Once we have a notion of conductance of a set, and we have an idea that we have this notion of a small conductance being clusterable, right? We can talk about the conductance of a graph. So this is the conductance of a set. So the conductance of a graph right? Again, if you think of conductance as the ability to send heat out, if you have a bottleneck, that's going to bottleneck your ability to send heat out. So you want to look at the smallest possible conductance. Right? Now, you have to make this sort of reasonable, right? If I have, there's a way to artificially make my conductance look very small. So how can I make my conductance look very small artificially just by choosing my set? I can make my set really, really big. If I make my set the whole graph, then there are no edges going out by definition, right? So this number is going to be 0. What I want to say is that the conductance of a graph is the min phi of S over all S subset V. But this doesn't make any sense because this number is always 0. I just take S to be equal to V. So intuitively, if you're taking a set and you're taking its complement, you have these two sets. What you should be doing is taking the smaller of it, not the bigger. Right? So what you say is that you choose it over all sets of V, where S is less than V over 2. I just wanted to say that. So you don't flip it around. It's just a convenient trick to make sure this definition makes sense. And this is the conductance of a graph. Okay? You can think of this as the best bottleneck you can find. Right? There's some set that really gets choked, right? That has nothing going out of it. For example, if the graph is disconnected, this number will be 0. Because there's a way to partition the graph into 2 parts. You take one component that has nothing going on with it. If the graph is kind of weakly connected, so maybe the graph looks like this, and it has a few edges, and it has like this, then you can pick one of those sets, the smaller one, and in fact you will get that low conductance value. So in some sense, you can think of conductance as a slightly more robust version of connectivity. Connectivity is very binary, right? Either it's connected or it's disconnected. One edge can change that. Whereas conductance is more of a smoothly varying parameter that allows you to say, okay, it's kind of connected, but not really. and it's, or even more connected, or highly connected. It's just a better way of saying it. All right? So intuitively, a graph that's well clusterable is a graph that has low conductance, because I can break it up into all these little pieces, and each piece works. And we'll talk about clustering graph. Yes, you had a question? Yeah.
Is conductance related to diffusion?
What's diffusion?
Differential diffusion kernel that we talked about?
No, it isn't. Well, in a spectral sense, these are all related. Diffusion kernels go directly to the spectral interpretation of a graph. We're talking about heat flow using the Laplacian. And it turns out there is a way to think about conductance using the Laplacian. So in a certain sense, yes. But this is a more combinatorial definition I can give you here. I don't know if it's a combinatorial definition of diffusion. It can only mean the spectral definition. Okay. So, since we're on the topic, let's talk about this. So it turns out there's a very basic inequality, that is a very well-known inequality, that allows us to relate, to understand what this quantity actually is. It's a very famous result. It's called the Cheeger's inequality. It's a beautiful result that has its origins in differential geometry and understanding manifolds, but has this nice graph theoretic formulation. So let's do the following. Again, so as always with graphs, it is very hard not to go spectral, because that's a very nice way to think about what's happening in a graph. So we have a graph, we have its adjacency matrix, and from there we can compute the Laplacian. There are different ways to compute the Laplacian. One way that we're going to use right now is, instead of saying that Laplacian is equal to D minus A, which is the diagonal matrix, we're going to do the Laplacian as is I minus, let's see, what I want to say is it D to the minus half or D to the half? It's D to the minus half. So it's D to the minus half, A, D to the minus half. You can see that if you take this Laplacian, multiply by D to the minus half front and back, you'll get exactly this. And this is what's called the normalized Laplacian. It normalizes the degree, so you get more of a random walk kind of behavior from this. So it's called a normalized Laplacian. It's not, there's another Laplacian called the random walk Laplacian, but this is slightly different. Okay, so it's basically like the Laplacian of the proof. And once you have a Laplacian, again, it's positive semi-definite, you can do that. You can start writing down as eigenvalues. So of course, its first eigenvalue will be 0, and no, yeah, so lambda 1 is going to be equal to 0, and there's lambda 2, all the way up to, I think, is it 1 or is it 2? 2. 2? Yeah, thank you. Just 2. So lambda n is equal to 2. Okay? And we know, for example, that again in this Laplacian, if you want to know how many connected components the graph has, you count the number of zeros. If you have 1 0, it has one connected component, i.e. it's connected. If it has more than 1 0, it has two connected components, and 3 or 4 or 5. Right? So if lambda 1 was 0 and lambda 2 was 0, it would have two connected components. The graph would be split apart. Suppose lambda 2 is very close to 0, but it's not 0. So the graph is connected, but it's very weakly connected. It might look like, that thing that I just erased. It might look like this. The one So in some sense, the closeness of lambda 2 to 0 is a way of telling us how close this is to being completely two separate components. In other words, the smaller lambda 2 is, the more this graph looks like two separate components. But wait, we already thought we had a notion of conductance that tried to capture that. But the smaller this value was, the more this looked like separate components. And the question is, are these related? And that's what Cheeger's inequality says. Cheeger's inequality says that yes, in fact, if you want to compute the conductance of the graph, you have to look at its eigenstructure. And it gives you a nice bound. Specifically, the bound you get, this number, in order for this to make sense, you have to realize that lambda 2 is less than 1. So taking the square root increases the value. Okay. This is a very cool result. Because what it's saying is that there is this combinatorial notion